Well, hey, thanks everyone for joining Mars University's first seminar today. We're really excited to kick off a new seminar series where we'll share meaningful conversations with leaders who are really pioneering humanity's effort to make life multiplanetary. Um, and this month's topic is on robotics and exploration, and we'll explore the innovation in the materials, environment, and mission requirements to successfully operate robots on the surface of Mars to really open up a new frontier for life in the solar system. And this is our host and moderator, Daniel Tompkins, who is our faculty for agriculture at Mars University. And I'll leave it to him to introduce our speakers and get us started over here.
Thank you, Cole. Yeah, so like Cole said, I'm a faculty for agriculture and working in agriculture for the last 10 years. I've seen a lot of technology moving into this field. So I'm currently right now, maybe the most involved in robotics and in space exploration. I'm also the founder of Grow Mars, which is focusing on in-situ resource plastic production, supporting agricultural base. With that, I'll introduce Dr. Michael Hecht, the principal investigator for the Perseverance's mission's Moxie project, the Mars Oxygen In-Situ Resource Utilization Experiment. It was developed in collaboration at the Massachusetts Institute of Technology Haystack Observatory, led by Dr. Hecht and the school's Department of Aeronautics and Astronautics, as well as engineers at NASA JPL. Prior to joining MIT in 2012, Dr. Hecht worked as a senior research scientist at JPL for nearly 30 years, if I got your bio correct. Good. And also would like to welcome Kris Zacny, who is the Vice President of Research and the Vice President of Honeybee Robotics and Senior Research Scientist. His interests include space mining, sample handling, soil and rock mechanics, extraterrestrial drilling, and in-situ resource utilization. And he also has a, I know of at least one hardware on Perseverance as well, the sample collection hardware there. So both speakers today have hardware on its way to Mars, and also more broadly speaking to the future of space exploration and robotics. So I guess we'll start off with
If I might say something, my
Yes.
hardware is coming back. Mike's hardware is gonna stay there forever. And that's a difference.
That is true. Awesome. And if you want to lead it off, Dr. Hecht, we'll begin with you in your presentation. Oh.
Thanks. That was making it a little hard. And thank you very much, Daniel, for the kind introduction. It's a privilege to be here, and I'm pleased to be able to have a conversation with all of you. I give lots of talks, but an opportunity to have a conversation is rare and is important. So what I'd like to do is tell you a little more about why I'm here. I mean, why you're spending your time listening to me and why that might be a profitable thing to do on this topic. And then I'd like to raise some discussion topics, some ideas. How do I put this? I'm a fan of really out-of-the-box ideas that are achievable tomorrow. Okay, I'm not so interested in anti-gravity and positron drives and stuff like that. But there's a lot of ideas that are not in the mainstream that are really exciting, particularly if you think like a Martian and don't try to think about transplanting Earth to Mars. So let me start by showing you why I'm here. And first I have to hit share screen. Let's start there. That's a good start. Okay, and so I want to focus on mobility in particular. So if we're going to settle into Mars, if we're going to establish a base of operations, I'm thinking like a McMurdo station, again, thinking near terms, not terraforming, but near term. What do we need? Well, I think one of the main things we need is to get around. And by getting around, I mean a few different things. We start with rovers, of course. Now, as I said, why am I here? I do have an instrument on the Perseverance rover, which is coming soon to a planet near you, landing on Mars on February 18th. This is really exciting. It's the second time I've been PI of an instrument on a Mars mission, and it's an extraordinary privilege and opportunity. So in this one, we're flying an instrument called Moxie, the Mars Oxygen ISRU experiment. And this isn't terribly exciting, but the trouble is you try to show pictures of an instrument and it's a box. It's a gold-plated box, so it's nice and shiny and doesn't radiate too much heat away. And it's got, of course, electronics in it and other parts. And it's sitting in the belly of this rover. And what's it for? Well, it's going to really represent the first major investment in situ resource utilization that NASA has made, as far as I'm concerned. And I bet all of you have either seen or read The Martian. Okay, if you've seen or read The Martian, you know the oxygenator, you know what it does. It makes oxygen out of carbon dioxide on Mars. And why do you need to do that? That's the question I want to address it for just a couple of minutes. And the main reason is that anything that burns fuel needs to breathe. And that's a very, non-technical way to put it. Fuel burns with an oxidizer. And by burning, I mean it reacts and releases energy. And there's a lot of different ways you can do that, but almost always that oxidizer is oxygen. That's why we call it an oxidizer. And we don't think about it on Earth. We don't think about it in this fireplace, in this lawnmower, in this airplane, in this automobile, or even in this human being. We burn fuel. We call it food, but we burn fuel. The oxygen that we need to burn that fuel weighs several times as much as the fuel itself. If you were carrying, if your car is carrying, 100 pounds of gasoline on any given day, you'd have to have several hundred pounds of oxygen if you had to carry the oxygen with you. And on Earth, we don't have to. On Mars, we do. So we want to make it on Mars because that's a heck of a large thing to have to carry all the way to Earth when you don't have to. So that's what Moxie is about. And so who burns fuel? Well, we do, but we don't burn very much. We're puny little things compared to a rocket, okay, that's going to lift the crew from the surface of Mars to orbit. That's the big customer, is that rocket, because that rocket, when it's firing, breathes, a million times as much oxygen as we do as human beings. Fortunately, it only fires for a few minutes, but it's still going to take something like 25 tons of oxygen. And a crew of 4 can get through a whole mission on half a ton. So that's what Moxie is about, using CO2 on Mars to create oxygen. Prior to that, my previous flight to Mars, if you will, my previous vicarious adventure on Mars was with the Phoenix mission, and Kris Zacny, who you'll hear from soon, was also involved with Phoenix. 2007, I led an instrument called the Microscopy, Electrochemistry, and Conductivity Analyzer. It was to look at soils, also in the interest of preparing for human exploration. And I won't talk about it. I'm happy to answer questions. But what was the main thing we found? Well, the main thing we found that was, from a chemistry point of view, kind of stunning. If you look at what's in soils in Earth, you find lots of chlorine, sodium chloride, and various other salts. They're everywhere on Earth. They're ubiquitous. Our oceans are full of salt. On Mars, that chlorine, instead of being in the form of chloride, seems to be in the form of perchlorate, like these green and red molecules here. The green is the chlorine atom, which is usually bare, and usually bare in a salt, and instead it's filled up its outer shell, in this case ClO4, with oxygen. So again, it's a very stable molecule, but it's ClO4. It has a lot of oxygen in it. And when it does break apart, it releases a tremendous amount of energy. You make fireworks out of it. So we've got this interesting stable chlorine molecule, chlorine-based molecule that has a tremendous amount of energy in it. It's very hard to harness that energy, but at least one person's done it with a biological fuel cell, John Coates at Berkeley. And this stuff is everywhere on Mars. You take a shovel full of soil and you have about 0.5% to 1% perchlorate. So that's the main thing we found. And so what do you start putting all these pieces together and say, hey, we've got oxygen, we got CO2 on Mars we can use to make oxygen. We've got perchlorate on Mars we can use to get energy. And we know, I don't have a picture, but you've all seen it. We know there's lots and lots of ice on Mars. Lots of ice. You have to travel to get it, or you have to dig to get it. I'm more of a fan of traveling to get it, because if you go up to where Phoenix landed at, even as low as 45 or 50 north latitude, you just scrape away a little surface soil, and there's lots and lots of permafrost, mostly ice right under the surface. So you've got all these ingredients, and I'm not going to say anything about this slide. Jerry Sanders prepared it, as far as I know, and it's just showing all the stuff you can make if you have some of these very simple ingredients, including both oxygen for rockets and methane for propellant. So you've got all this stuff. So let me segue to the main topic I want to just suggest, because again, time is short here. Mobility. Well, where do we want to go? Okay, start with where we want to go. Surface transport. We want to be able to drive. Okay, I mean, where would we be without our cars? We want to be able to drive in a convertible, if you will, nearby, in a spacesuit, for local travel, to check out equipment, to do some exploration, collect samples, whatever. And then you want to have long treks where you may be going to, look for resources or do longer term exploration. As was described in The Martian, you want an environmentally controlled rover where you can take off your helmet and relax and breathe. Suborbital transport isn't talked about a lot, but boy, if Mark Watney had something that could go suborbital and hop across the planet, it would have been a very short book. And that's been thought about. And why you might want to relocate, you might want to live on the pole for a while, and then when winter comes along, you might want to move to the other pole. You might want to use it simply to retrieve blocks of ice from icy places and other resources, or simply to explore other parts of the planet. And then, of course, ultimately, you do want to come home, and being able to go from surface to orbit, that's what Moxie is addressing. So I just want to end then by suggesting a number of unusual ways we could go about this. And most of these I've actually proposed. Most of them I've proposed, for funding and lost, because it's hard to sell out of the box ideas, but I'll talk about them a little bit. So, the usual suspects, of course, solar power we use on most of our missions. Radioisotope power we use on of course, Perseverance and on Curiosity. And then the new thing will be kilopower reactors. These are already being tested. These are actual nuclear reactors that are small and safe and can fly to Mars and put out kilowatts of power instead of hundreds of watts. And that will be a game changer, honestly. But there are also sources that are more native to Mars. And I've talked about one, of course, this homebrew propellant, which starts with Moxie to make oxygen. And then you could, if you dig up water resources, you could start using Sabatier and other reactors to make methane. And before you know it, you're making vodka. There's that whole line. Wind is something we've actually proposed, wind turbines for Mars, because Mars solar doesn't always work on Mars. There is a nighttime, there are dusty days, and one of my major interests is in polar science. And if you want to be on the poles in the winter, you don't have enough sunshine. You don't have any sunshine, and you don't have enough light to drive solar power. So the solar panels. So wind for Mars is achievable. It's practical. Space solar, I've been pitching for a while without a lot of success. But to me, this is really the single most compelling energy system for Mars, and particularly for mobility. And the idea simply is you have an orbiter with solar panels. It doesn't have to be huge at all, it turns out. It's in a low Mars orbit, and you transmit power from orbit to the surface with lasers. These high power lasers already exist. There's fiber lasers that can transmit kilowatts, and you can collect them on solar panels on the ground. And you could recharge a rover periodically by simply hooking up to an orbiting power station. Moxie, in addition to oxygen, makes carbon monoxide, CO, which is a fuel. It's not the greatest fuel for an actual rocket ship, but it's been looked at seriously as a fuel for something called a hopper, which is, not even quite suborbital, but it's something we'll take off in a rocket and land somewhere many, many, many kilometers away. And that's another out-of-the-box solution you get more or less for free when you're running oxygen ISRU. Another technology that's been dabbled in at NASA labs and universities is lithium CO2 batteries. I was looking for a picture and I came up with this wonderful little website that said lithium CO2 batteries promise 7 times the energy density of lithium lion. And I really wanted to find that lithium lion and see what kind of energy it has. But the point is, CO2 is native. This is ISRU. You bring lightweight lithium and you have a great power storage solution without a lot of mass. And finally, there's the perchlorate biological fuel cells I mentioned. So here's 6 ideas for generating or storing power on Mars. There are more. There's lots of electrolysis fuel cell combination systems that could store, store power in liquid form on Mars. But here's a few, and in my mind, this is the key to humans and robots and mobility and working together, is being able to have power where you need it, when you need it, and be able to deliver it in not just in a fixed station, but in a mobile platform. So hopefully that's some food for thought, and I'd love to have questions and discussions on the subject.
Thank you, Mike. Greatly appreciate your presentation. And I think we'll have Kris present and then we'll get into some discussion, if that's okay.
Can you see the screen?
Yep.
Fantastic. So Mike, nailed it. Essentially, we call it in-situ resource utilization. You come to Mars and you want to live off the land. You want to significantly reduce the amount of resources that you have to bring with you to Mars to sustain your presence. And in order to come back, imagine that you explore a new area here, and you have to bring all the supplies with you, like very first explorers, right? They were unable to bring everything, but as they were venturing west in US, they were so-called living off the land. They were harvesting the local food and exploring. The same thing we have to do on Mars for Mars exploration to be fully sustainable. The ISRU is a key, and there are 2 things I wanna say about it. First one is a lot of technologies that we have developed here, terrestrial technologies that we have developed, could be used on Mars with some modifications. So lubrication on Earth, it's gonna be wet lubrication. On Mars, we'll have to heat up actuators, but actuators could be very, very similar. So the step between Earth and Mars is not actually as big as as we initially think. And it's also extremely important to test selected technologies under analog conditions here on Earth. And I'm going to present to you a couple of pictures of analog sites that look pretty much exactly like area on Mars. But it boils down to the thing that if you develop technology that will have to work on Mars, and this technology fails while digging a hole here on Earth or performing mining, 100% it's going to fail on Mars. When you want to, for example, drill a well to get water. You pick up a phone and you call local company and you say, hey, I would like to drill a well to the water ground and pump water to the surface. The company doesn't tell you that, yeah, sure, I'll come and there is a 50% probability that actually I'll drill a well. They're gonna tell you, well, I've got next window next week, Tuesday, and it's gonna cost you $5,000. No one is asking you or telling you that this is 50%. They're 100% sure that if you ask them, they're gonna come and do the job. So when we go to Mars with the technology, we have to be as certain, okay? It's not gonna be if. Well, the technology simply has to work because it's absolutely crucial technology to sustain human presence. Mike mentioned Phoenix. This was absolutely phenomenal mission back in 2008. Landed in the northern parts of Mars. What you see is the extent. As far as you can see, it's a reddish soil with rocks. If you were to take a broom and sweep first inch, what you'll find is these bald spots. And the picture on the right-hand side, these bald spots were blown away by a rocket thrust. So actually you could see underneath, and that's ice. It's pure ice. You can dust it off and they have an ice hockey in this location. And as Mike already mentioned, it's perchlorate mixed with water and soil. This soil and the icy soil and ice is as hard as rock because it's very, very cold. It's cryogenic. But this was the very first time where we landed on a Martian ice, and we actually dig into it and tasted it. Well, if you look at the dry valleys of Antarctica, and one of these red jackets over there, it's actually me. Same thing. You see rocks, you see reddish soil. If you dig a couple of inches below the soil, you get ice cemented ground and you get ice. The similarity is just absolutely unbelievable. On top of this, dry valleys is high up that you're not gonna get liquid water forming any day of the year. That's why it's called dry valleys. So the ice and the ice cemented ground that you see, it's vapor deposited ice, similar what you're gonna find on Mars. So if you need to test piece of hardware, the goal is to bring to locations like this and give it a go. And if it works, then you have a shot to do this on Mars. But if you fail, oh boy, you've got work in front of you. So currently we are developing technology called red water with a goal to drill around 10 to 20 meters through the dry layer and get into the ice sheets. On the top right-hand side, if you can see my pointer, imagine this is a drill. For scale, this blue stuff is actually ice. This is picture taken on Mars. And that's around 100-meter layer of ice. So idea is you're gonna drill through probably 5 to 10 meters, get to ice, and then warm up ice to form liquid and pump it to the surface. The technology is called red water. It uses essentially two terrestrial technologies that are working every single day. The first one is called cold tubing. It's a metal tube, sort of like a Home Depot tape measure, but instead of a tape, it's essentially a tube. This tube is wound like a garden hose on a drum. You're sending it through so-called ejector, which straightens this steel tubing into absolutely straight pipe. And you use this pipe to drill below the surface. So that's what we're using for red water. And then to melt and pump water, we're using technology called rod well or the Rodriguez well. It's being used in Antarctica, in the South Pole, to provide fresh water to the folks who are already living there throughout the year. So by combining these two technologies, two robust technologies that have been working here on Earth for a long, long time, we're forming red water. We develop prototypes And pictured on the right-hand side, you have this big block of ice in our freezer at around -25°C. And within 15 hours, we essentially generated 90 kilograms, almost 100 kilograms of water to do at 35% efficiency. So to mine, say, 3 tons of water, this is what NASA requested, it will take us a month with this sort of scaled down version. So you can see we took terrestrial technologies, cobbled it together, and developed something that is already successful in a laboratory environment. So there are many other technologies that you can spin off for Mars, but it's a first step to do so. So with this, I'm gonna stop here, and we can start discussion.
Thank you both on the presentations. To start it off with, I'm not going to do any slides real quick, but as faculty role, I just wanted to discuss, the role of agriculture on Mars, which seems like a pretty, why agriculture on Mars? And, we often forget that all the things that agriculture provide, right? They provide on Earth, wood for building material. They provide, agriculture provides crops for food, and it also provides ecological services for clean air and water. And agriculture can do all of this and more in space where there aren't these resources necessarily readily available. So, looking forward to, covering the emerging science of lab-grown food and synthetic biology and greenhouse optimization. But really what we're able to do is enable on-site manufacturing. Once we get there, we're able to, for instance, produce, a significant amount potentially of plastic, in a relatively easy way, using the resources of water and CO2. And I guess to start it off with, we were discussing a little bit before this, how the materials that we send to Mars right now are kind of flight derived versus what's needed on site. What materials do you think produced on site would enable robotics and enhance human exploration, coupled with robotics, I guess?
I'll tell you something that I'm really fond of, and Mike, we discussed this with Mike, 3D printing. And there is a lot of technologies that are being built right now for 3D printing using Regolith. There is a lot of this going on for lunar exploration, 3D printing structures on the moon, habitats. We had a project related to 3D printing structures in space. So mining dust from asteroids and creating structures in space. And on Mars, that's also feasible. Prior to this, the workshop, Mike and I were discussing how much it takes to essentially to build a piece of hardware. And you essentially have to hire a structural engineer to figure out how to build something that's not gonna fall apart on top of a rocket, and that's not gonna fall apart while during a descent and re-entry on Mars. Because these vibrations and shock and the vibrations are absolutely phenomenal. And you essentially trying to figure out, okay, I need so much metal, but not too much, because then I'm gonna be too heavy, and my instrument is gonna get descoped from emission. So it's really, you have to, the balance is absolutely unbelievable. And you're doing it only so that you get to Mars. Once on Mars, you don't really care how strong the stuff is, because you don't see the same vibrations and shock amplitudes and this sort of thing. So now, if you do 3D printing using Martian regolith on the surface of Mars, you can build structures that are designed for Martian gravity and the forces that they're gonna see on Mars, and not the forces that they're gonna see on top of a rocket and during re-entry. So I think this is gonna be a big game changer. Again, comes back to this live off the land motto.
And of course, we can do this on 2 scales. There's the scale that Kris is describing of things, instruments, chairs, things that you'd make in 3D printers. And there's also a large scale for fabrication, for building materials. People have looked at building roads and walls and buildings and by techniques that essentially are large scale 3D printing, starting with, well, of course, right now a lot of the focus is on lunar regolith, but on Martian regolith as well, and making cement and making bricks and putting them together and making roads. And that will be an important technology as well, because that's stuff that is just not so much as too fragile to bring, it's just too big and heavy to bring with you.
Exactly. One of the projects we had a while ago is how to prepare landing pads. Landing on Mars with rocket thruster is actually relatively dangerous because of all the plume interacting with soil and damaging the spacecraft itself. On Curiosity, weather station was damaged because of that. The small rocklets got caught up in a rocket plume, went around and hit the weather station on top of a Curiosity rover. So before landing, so everything went fine. The instrument worked up to the moment where it's supposed to land. And during landing, half of the instrument capability of the instrument was damaged during the landing itself. So a lot of folks have been looking at developing landing pads to alleviate this problem. And one of the solutions that we are looking at is essentially, initially we thought it's an absolutely crazy idea, but then we found it actually works. The idea is to weld two rocks. You pick up rocks, and there's plenty of rocks on Mars. You take one rock, you attach it to another one, and then you essentially melt the contact point between the two rocks, forming this glassy structure. So essentially, we're welding two rocks. And it's actually, when you start welding rock after rock after rock, you build something that's pretty strong. So this was designed for landing pads, but it could potentially be designed to build habitats as well. So that's just one idea that initially was crazy, and then we ran the tests, and it actually worked.
And when you start making habitats out of materials that are so massive, you actually can start talking about serious radiation shielding, which of course is an ongoing challenge on Mars. Now, as I said, I like out-of-the-box solutions, and so another way to do this is to take an entirely different strategy with respect to where you land on the poles, and people that live and work in polar areas realize that all you need is a chainsaw, and you can start making large blocks of ice and build structures out of it. And that, by the way, is excellent radiation shielding. So there are some innovative ways to think about using materials just based on where you go.
Exactly.
As we bring materials there, it seems like assembly on site has a lot of benefits. Having the robots not necessarily in their final configuration, but really having a shelf of motors and servos and really fabricating on site. Any thoughts into repurposing some of okay, you have a robotic mission to do, one mission, can you salvage that and kind of reuse it again and reconfigure it? Have there been any hybrid kind of solutions for future missions?
It's a smart way to design. Even when we design a mission, and the mission is very complex, has a lot of actuators, we put in a lot of effort to make sure that the number of different actuators is absolutely minimized. So we qualify maybe two type of actuators, and then we apply them to different robotic systems. And that's a smart way to do this. And on Mars, that's how I think we're gonna have to do. The issue is some actuators, we're gonna see significant amount of wear and tear. Wheels, for example, they're rolling all the time. Every time you roll, it's millions of revolutions. And sooner or later, this stuff is going to cease and break. It's just matter, it's not if, it's when. And we can actually predict, with a pretty high certainty when this is going to happen. On the other hand, you have robotic arm actuators. And these robotic arms do not actually see a lot of revolutions because you don't use them that often. So what you can do is when you 20% before the end of the life on your wheels, you switch, okay? You put the wheel actuators into the robotic arm actuators, and you take robotic arm actuators, you put into wheel actuators, and you almost, not double, but almost double the life of a mission.
You mentioned robotic assembly, and that's, of course, a superb way to use robots. They're very good at it. It's very tedious for people to do it because they know what they're, you can define the tasks, you can define the objects that are being picked up and moved and assembled and welded and whatever. What is much harder is dealing with raw materials. And just looking at the recent history of things we've tried to do robotically on Mars, we've been talking a lot about Phoenix, and we did manage to use a robotic arm to dig a trench about so deep it took 2 weeks. And that was a job that a toddler could have done with a plastic pail and shovel in 15 minutes. And then we tried to do things as simple as taking a scoop of loose soil in a robot arm and then dumping it out. And it didn't dump out because there are strange adhesive forces on Mars that we're not used to on Earth. And it seems every time we try to deal with materials in sampling, I could tell 10 more stories, we're surprised at how difficult it turns out to be. Now, people would solve those problems. We're very good at solving those problems. Robots, not so much.
Another key, moving beyond kind of the hardware and material constraints, looking at, what really excites a lot of people in agriculture, especially with image processing, is the cost and the speed of processing and how that goes along with robotic operation. I'm not too up to speed on this, but I imagine radiation hardened processors are a limitation on Mars for running some of these more autonomous features. Do you see kind of a data center in a radiation shielded area where it doesn't, like the data center is not rad hardened, but then the robots are sending data and communicating that way, and then you kind of your microcontrollers, you kind of have a stack of microcontrollers that, okay, if that's not where the real capital is. How do you see the challenges of future robotics and limitations around rad hardening?
Well, rad hard components, that's a controversial subject. I think it's often misunderstood subject. The surface of Mars actually isn't too bad. And, I've had instruments that have used commercial electronics extensively. There are some things that are particularly soft, but most normal components will survive just fine on the surface of Mars. First of all, you've got the planet itself blocking half the radiation. You have some blockage from the atmosphere. Being in orbit is a lot worse. And very often, because rad hard electronics are not only very expensive, but have very long lead times, and they're often in big, awkward packages that are fragile, people will instead design with conventional components and put in a lot of redundancy, or put in current monitors to watch for latch up and other known failure modes, or just do, again, redundancy and voting. You have three computational circuits, and you verify that they give you the same result, and if they don't, you take 2 out of 3. And so there are many techniques to get around the radiation hardness issue, and again, on the surface of Mars, it's nowhere near as serious as in deep space or in places like around Jupiter.
Yeah, I would second that. In many cases, in critical cases, you really need this redundancy. So when you're launching a rocket, you obviously want everything to happen smoothly without any problems. But if you're roving, there are many other ways to say, oh, something is not right, and essentially reset, computer A while computer B is still working. And a lot of activities on the surface of Mars would be slow. You'll have a time to check if everything went fine, and it's not the same as certain critical functions that have to happen. For example, during EDL or during launch, where everything has to happen, otherwise the rocket is not gonna reach the orbit.
And simply having an astronaut in a habitat with a magnifying lens and a soldering iron and a stack of chips can tremendously simplify a process that right now relies on being every board, every component being absolutely bulletproof. You don't need to do that if you can fix things from time to time.
Yeah.
Excellent. Well, Cole tells me that we do have some questions from the audience, so I'm going to have Cole ask those. That's okay.
Awesome. Thanks, Daniel. I see a question here from Sammy for Kris. What are the biggest challenges your team faced designing and building a drill specifically for Martian conditions, as opposed to designing such a drill for water extraction on Earth?
Oh, probably the biggest challenge is money.
Yeah.
There are two things: mass and cost, and a good system engineer can trade the two. But very often, and I've seen it as we're sending more and more stuff. There is a big pressure to make things less expensive and less expensive. So I think trying to find innovative solutions to do the same thing at the reduced funding level, I think is really, to us, is really, really tough. But so big thing is cost, and the cost relates to your design choices or engineering choices, where you can sort of reduce analysis to cut down on cost, or use less expensive material or components, and where you actually have to put more money to develop something that's more robust because it's more critical. So that's one thing, and obviously, second, really, really important aspect is testing. And very often, it's not. What I found is testing is significantly more expensive, or becomes more expensive than building a hardware itself, because you need to go through pathologically worst cases. You really throw the worst at this piece of hardware because you really want to make sure that it's going to work. And testing costs money. And if something breaks, you have to stop, you have to fix it, you have to find out why it broke, you have to go back, do a redesign. So testing is, if you look at the cost of the hardware, testing is significantly more expensive than actually building the hardware.
Yeah, you can make the hardware out of solid gold. It wouldn't make any significant impact in the cost of the development whatsoever. But let me tell a little story that illustrates some of what Kris is saying. In-Sight, the In-Sight mission has a probe. It's essentially a sort of a hammer, an impact hammer type drill. They describe it as a self-driving nail, but it's an impact hammer. And this was tested extensively at JPL in big systems and big vacuum systems. And one of the things they found is that even though this thing works just fine, drilling holes through large columns of soil, as soon as you lower the atmospheric pressure down to something close to Mars pressure, I don't think the break point was 100 millibar or something, it stopped working. And it was really mysterious why it stopped working. It was reproducible. And it turns out when you do something like impact hammer drilling, you're relying on shock waves and air to carry a lot of the force from the drill head to the material. And if you take away that air, it stops working. And then eventually they did get it to work, and they changed the design. And of course, now there it is on Mars, and it's dealing with Mars soil, which is not, none of us have held this in our hands, and it's not well understood, and it's not working as designed even then. So even with all the testing, there's no substitute for testing on Mars. And that's, I look forward to Kris's drill being tested on Mars. And I'm very grateful that Moxie is being tested on Mars for the same reason. We will have surprises.
Yeah.
Very exciting. And here's another question from Jin. How does a strategy, or actually from before that, Anthony asked a question for anybody: why aren't electric rockets being looked into more seriously? And he mentions the rocket could charge as it's traveling to Mars and bring back not only a recharged engine, but also recharge batteries for on-planet energy consumption.
Well, we certainly are using electric propulsion, ion engines on missions currently. So I think it's not only being looked at, but it's being used. And it may be the optimal technology if we want fast passage to Mars. There's only so fast you can go with chemical propulsion and hard acceleration at the beginning. If you want to really accelerate to high speeds, doing a slow but continuous acceleration over a long period of time with a electric propulsion is the way to go. So I'm not sure I agree it's not being looked at, if that's what it's referring to.
Okay, thanks. And then Jin asked, how does the strategy of building a landing pad before landing compare to the lunar Starship strategy of switching to braking rockets in the nose at the last few seconds so that the exhaust plume is not too close to the ground?
It's just a different architecture to do this. But now you have to put retro rockets in the nose cone as opposed to down below. So that's a reason why it was done in the first place. So you had to design your landing spacecraft, right, to accommodate or try to alleviate this problem. But now, remember, on a Curiosity rover, your thrusters were 10 meters in the air, okay? They were not right next to the surface. They were 10 meters above the surface, and we still damaged the weather station. So I don't know how high you have to go to alleviate this problem, but it's definitely a problem. And I'm sure folks at SpaceX have been looking at this for a long time.
Of course, the moon, you mentioned the lunar strategy. The moon has a unique problem that Mars does not have, because not having any atmosphere, something can go into orbit 10 feet above the ground, conceivably. And there have been analyses showing that if we start landing on the moon with any regularity, with large payloads, with large rockets, you will start sending debris orbiting around the planet at an altitude that will cause damage. And that literally we would be creating a significant risk by landing without a landing pad.
Right, you can send blast gateway this way. Yeah.
Awesome. And I think there are 5 or so more questions. I'll let you guys ask them yourselves.
See, I don't think we have access to the Q&A. Are they just in the chat, or?
Yes, yeah. Whoever asked the question, feel free to voice up and ask your question. You should be able to unmute yourself and share your screen if you'd like.
Hi, I'm Sherilyn Young, and PhD crafts chick, and I was just really intrigued with what Dr. Hecht was saying about the adhesive forces, and I was wondering if you have a good reference for that so that we can we can read up later or anything like that, but Crafts Chick was extremely intrigued. So thank you.
Well, thank you. And, I
Yeah.
think I'm almost embarrassed that the answer is no, this is anecdotal.
Okay.
Chris remembers it. In fact, what I remember about it, that particular incident, is that, one of the things you have to recognize is that it's not readily recognizable when you're operating robotically on Mars the way we have in the past, is you have to take everything step by step and verify on the ground that it's successful before you can do the next step. So when I say we pick up a scoop of soil and dump it out, what we really do is pick up a scoop of soil, take a picture, look at it overnight, and come back in the morning and try to dump it out. That's what you have to do. And so that was really where the problem came about. And as I recall, half of the scoop was in sunlight and half of it was in shadow. And it was the sunlight, the sunlit part that stayed in the scoop and the shadow part fell out. And whether this was the perchlorate potentially interacting with frost that had that had settled in over the night and creating sort of an adhesive, because perchlorate brines have amazingly low melting points, so you actually could get some almost melting and create brines, or whether it was just what we call van der Waals forces because things are so pathologically dry and they dry sinter. We're only guessing, and it would be fascinating. I'd be fascinated in understanding it better, and I'm sure Kris would as well from a excavation and manufacturing point of view.
Yep.
Okay, thank you. Because I was just thinking, more like, micro, like how would sewing machines work? How would knitting and crocheting work? Tension, various,
Yes.
Various fabric tensions and everything. It's like, you embroider with linen embroidery thread, and DMC had a line of linen embroidery thread for a couple of years. It was the creepiest stuff to work with on cross stitch, because you would make the cross stitches and the linen thread, the linen floss would expand to fill the 4 little holes of the counted cross. So, I'm geeking out at a weird angle, I know, but thank you.
Well, no, in fact, one of the things you learn, I used to be in surface science for many, many years, studying surfaces and materials. And one of the things you see is that everything we look at, everything we handle, every piece of fabric, every material is normally coated with several monolayers of water. It's called a capillary layer of water. And actually, if you come in with an atomic force scale probe and then pull it out, it's like the water is sucking the probe back toward a surface. When you get in a vacuum or even a near vacuum like Mars, that is no longer true. And because you don't have that layer of water on everything, I mean everything, materials interact differently, and there are different forces that come into play.
Okay, thank you so much. Truly appreciate it.
Okay. Here's another question from Ailes. Is anyone considering contactless plasma drilling on Mars?
Yes. You need a lot of power. The thing about plasma and for like melting and fracturing, you're changing you do the phase change of a material. And if you do phase change of a material, you're putting significant amount of energy. You have some plasma drills that try to fracture material, but those sort of work when you have minerals within a rock that have differential coefficient of thermal expansion. So this sort of works on rocks that contain quartz, because quartz crystal structure changes at around 700 C, induces fractures and rock breaks. But in general, it's just very, very power intensive.
Awesome. Thanks for that. Looks like we're running out of time here. Do you guys mind another 5 possibly 10 minutes to help answer these?
Sure.
Sure.
Okay. Awesome. And again, if anyone wants to ask a question verbally, feel free to share. Jump on.
Cool.
Okay. One question was for Kris. What are the benefits of standardization in construction and robot automation technology?
I think it's a must, really. If you look at the Mars exploration, it's not just U.S., but you have many other countries. In fact, China is going to be landing, U.S. is landing, Europe missed the landing opportunity because of COVID, but you would have essentially 3 rovers landing on Mars, in the same time, and it's just going to get busier and busier. So sooner or later, these robotic systems will be collaborating with each other. So having some kind of a standard, system that's where your robotic systems are designed with the same standard is very useful, because this will allow them to cooperate and collaborate together.
There's only one case I know of where I think we've done that well for Mars exploration, and that is in communication, back to Earth. That if you're on the surface of Mars, it's tremendously energy intensive to talk directly to Earth. So almost all the communication to surface assets are through orbital relays. And each spacecraft that flies into orbit on Mars, whatever country launches it, has a compatible relay. It used to be called the Mars Balloon Relay, as I'm sure Kris remembers, because it was developed for a Gondolfier experiment, I believe. It's no longer called that. But if you're operating on the surface, say, as Perseverance will be soon, we communicate back, we will communicate to Earth through Mars Odyssey, through everything from Odyssey, MRO, Mars Express, Maven, whatever spacecraft is up there has a compatible relay to get back to Earth. That's been of tremendous, tremendous benefit to any number of missions.
Hey, Mike, I see a question that it's up your alley. Is there a strong case for wind power generation on Mars?
That's that is a fascinating one. Again, I have put in with colleagues, put in a proposal a few times. My personal interest is I want to send spacecraft to the poles. And of course, when it's, first of all, when it's dark, you can't use solar power. We use radioisotope power very sparingly. And if you want to do experiment on the poles, the last thing you want is a big heat source, which the radioisotope would be. So that would be a very strong scientific case. But pragmatically, unless you're using nuclear, okay, you're dependent on sunlight. And you don't always have sunlight, just as you don't on Earth. So I'd say there's a very strong case. Now, what can we practically do on the scale of a lander like Phoenix? Our estimates are that we could, with about a 5 kilogram system, generate about 5 watts if there are 5 meter per second winds. So we think of that as the 555 configuration. That's not a huge amount of power, but it's more than enough to keep certain basic functions alive. That's the only downside of wind, is that the systems tend to be massive.
Is the temperature a limitation for the computer systems, or are there?
For wind or
for robotic operation, would there still need to be a heat source to generate the heat required for the computers to operate?
Well, thermal management, I think generally not for computers, no, because they generate more heat than you have to shed heat from most computer systems. They generate waste heat by themselves. Batteries tend to need heat to keep alive. And there's survival heating that's often needed for electronics when it's not running. And again, it all comes down to power. It all comes down to power. You know, I didn't really answer the question about the low, now that I see the low atmospheric density in wind. It's a little bit subtle. The wind power is going to go as the cube of the wind velocity. Okay, winds tend to flow much faster on Mars than on Earth. So when all is said and done, when you fold everything in, you get about half as much power out of the wind on Mars than you would on Earth under typical conditions. And not coincidentally, you get about half as much sunlight incident on Mars in terms of power as you do on Earth, because ultimately it's solar power that drives the winds. So it's not a coincidence.
Fascinating. And it was a last question from Jin. Are there any data on lithium abundance in Martian regolith?
I don't know of any, and we've assumed that it is very, very rare, very trace. And when I say we've assumed, when the wet chemistry experiments I described earlier, we actually used lithium as a calibration reference. So we intentionally added a little bit of lithium because we knew that was the last thing we'd expect to find. So the reason I was mentioning lithium batteries is because it's very, very light. It's about the lightest solid element there is, and the beauty of the lithium CO2 system is that the CO2 is the heavy stuff, and that's freely available. So the same way we rely on oxygen, which is heavy, on Earth because it's freely available, you can rely on CO2 reactions on Mars, and you just bring the light stuff along with you. In this case, the lithium.
Awesome. Okay. I don't think there are any more questions over here.
Yeah, Cole. Hey, Cole, if I could address the power issue. Most of the time we're talking about small spacecraft built and launched from Earth, and they're powered by solar panels or RTGs, which are fairly low power. But someday we're hoping to have a settlement on Mars with a lot of power in some way. It might be, say, nuclear breeding reactors running on thorium. And if we have enough power to, say, manufacture polymers on site and other materials, then we might also be able to run plasma torches, laser cutters. You'd want to manage them. So you might say, okay, at this time of day, we turn off this production and we turn on the plasma torches. But this is a ways off in the future. So for now, we are relying on very low power solar panels and RTGs. That's all.
And it may not be that far in the future. NASA's already testing kilopower reactors that'll put out kilowatts. And of course, many nuclear reactors have been flown in the past, mostly by the Russians. I think the U.S. has only flown one.
Yep.
So it's not a brand new technology. It's obviously a politically sensitive technology. But one of the things I'm fascinated by is even if you had nuclear reactors providing the base with power, you still need to think about how to make that power portable, how to bring it to other places, how to drive with it, how to transfer it. And I think that's a very rich potential research area.
Exciting. Well, thanks so much to our speakers, Michael, Kris, and Daniel. Keep up your wonderful work over there. Keeping on, and really appreciate everyone's time and joining us this Friday.
Yes.
Keep asking questions. That's
Thank you.
All we can ask. Thank you much.
Yeah, very much enjoyed it. Happy holidays, everyone. Bye-bye.